that you saw earlier on the zigzag one. And we expected when we react it with the carbon nanotube or the peroxide that we'd get some formation of epoxides and carbonyls, as well as a burning reaction where carbon is removed from the carbon nanotube to make CO2 gas or something of the like. And this would make a hole on the nanotube. So we looked at this unit cell here, which is 2 units of the carbon nanotube long, and it has 16 hydrogen peroxides around it. And we ran a dynamic simulation for that. And one interesting part here, you can see the reaction between the hydrogen peroxide, one of the pathways here. The hydrogen peroxide breaks and a hydroxyl group goes and forms with the nanotube, which is one of them that I did not expect to happen. And in this still frame here, it's kind of hard to see, but the 6-member ring on the carbon nanotube was functionalized with 3 different oxygens, and it actually broke and created a hole on the nanotube without dissociating a carbon off of the nanotube. I also looked at the system under both cationic and anionic states. The anion is here, and we see more reaction, but nothing like the cationic state where the whole nanotube kind of just breaks apart. And the ionic states we looked at are probably more than you might expect to find in a regular lab experiment, but it will give a good approximation of what we can do with a more limited time. So what we did see was reactions that I didn't expect. First off was the hole with no leaving group. We saw an epoxide form, and it was stable for hundreds of femtoseconds, but ultimately it did go to form a carbonyl. We kind of saw maybe a little bit of the burning with the cationic state, but not really anything like I'd expected. And then hydroxylation and hyperoxide formation that I didn't originally expect, but we saw those as well.
Okay, let's thank Brendon for a very interesting presentation. And this study of exotic regimes of reactions is open for discussion.
So I have a question.
Please.
Can you go back to where you have the charged species?
This one?
Which one is which?
Oh, this one's anionic and that one's cationic.
Why is it the cation?
So
How do you create the cation?
Well, the way we did it was artificially removing or adding electrons, but I think the thought is that could model Lewis acid.
On a molecule, on each of the molecule, I mean, it's a single cation or what?
cell.
Oh, it's largely ionized, like more than 10 electrons, like 16. 16 out of like 300 or something.
So do you have any rationales between why one broke totally apart and the other one kind of didn't see much?
I think it was, and I looked at it, but it was a while ago. I think more of the electrons, like the change in this one came around in the solvent, and that one it was more on the tube itself.
So, functionalizing the carbon nanotubes with oxygen, you can directly use anionic oxygen. Was there a specific reason why you have to use hydrogen peroxide to functionalize the carbon nanotube surface with oxygen?
That's just what I was looking at. No reason specifically, no.
Would you consider this more as a gas phase or more like a liquid phase?
Oh, this was probably gas phase because it was very hot, like at 2,000 Kelvin, and maybe it could be a liquid at pressures, but gas.
Okay, let's thank Brendon once again. And the next presentation continues the subject of the electronic properties of functionalized carbon nanotube. And the presenter is Whitney Hong. So she will look more on the electronic structure side of the carbon nanotubes functionalized by oxygen.
Hi, I'm Whitney. So today I'll be talking about the oxygen absorption on single carbon nanotubes. So first off, I will go through the introduction and I'll talk about the motivation of this project, and then I'll talk about the methods, result, and then finally the conclusion. So first off, the introduction. Carbon nanotube is a folded sheet of graphene, a sheet of carbon.
I just have a suggestion. Since he already introduced it, right? We
Oh,
probably
yeah.
can skip it and save time for results, right?
Okay, and then some of the applications including electrochemical gas sensors, and they also use in polymers to control and enhance conductivity. They are added to anti-static packaging. So why am I talking? So for gas sensors, it can induce a strong change in conductance, and then the carbon nanotube can be used to detect gases such as NO2 and NH3 or oxygen, and experimental data has shown that oxygen increases conductivity. So we are using computational methods to look at this thing. So I use, to build and edit the models, I use Avogadro, JMOL, and VASView. And when I run the jobs, I use the VAS software. And then I use a 3-unit cell of carbon nanotube folded at 40, and I manipulate the position of oxygen on the carbon nanotube. So after optimization, I found out that the band gap of the modified system definitely decreases compared to the pristine. This one I have one of the carbon substituted with oxygen, and a few other cases where I have just one, I remove one carbon from the nanotube and just have one oxygen molecule on top of it, and the other one I just put either parallel or perpendicular to it just to look at the result. And the band gap definitely decreases significantly. And then when you look at the absorption spectra and the molecular orbitals, for the pristine structure, we have the absorption spectra at 0 frequency, but for other systems, they decreases significantly for the absorption spectrum. So in conclusion, the oxygen definitely decreases the band gap and thus increases the conductivity. The change in absorption spectra also proves that oxygen is present.
Okay, let's thank Whitney for interesting presentation and for being record short, which is very appreciated in our circumstances. And her presentation is open for discussion.
On one of your tables, you had log of A. What does that mean?
So So the A is the absorption at 0 frequency, but because it's too small to measure, so I use logarithm.
More questions?
Could you provide more analysis, like you were putting these different alignment, different positions, right? And so you're saying, okay, electronic structure is definitely a factor, but this is very trivial result. You can say it without doing any calculations, right?
Yeah.
So maybe you can give a little bit more physical or chemical explanation, like in which case, which one is, why is this or that, right?
So for sure we can see there's difference like the oxygen definitely affect the density of states.
Like when you compare, for example, substitution of oxygen versus just attachment of O2 molecule, disabsorption of O2 molecule, right? In both cases, your gap is decreasing, and right? But is it the same nature, any difference in electronic structure between these two cases? Or it's exactly the same behavior? In other words, can you differentiate these two cases just looking on your electronic structure somehow?
Not really, I don't think so.
But do you expect it should be different or something should be different?
No, I was hoping to have more time to look at other ones, but I only managed to get this much information result.
But did you take a look on the orbitals localization? Maybe this could give you some ideas,
So
right?
for the HOMO and LUMO, it does not change a lot except for this one. It has localized orbitals on the oxygen.
In which case, when you substitute or when?
No, the one that I put on top just the normal.
So when it's phase absorbed, then you have very strongly localized orbitals. And these orbitals introduce this closing or this size inside the gap, right? In the other cases, when it's substituted, it's more delocalized over the surface, although the gap is still changing.
Yeah.
Okay, so you have a different nature of these electronic states. Okay.
Thank you.
Dr. Kuhn?
So what happened? So for the undoped system, it's a semiconductor, right? With a finite band gap, right? So that's true. That's true.
How large is the band gap for undoped system? What is the gap?
Yeah.
Yes,
The
approximately.
energy gap. The energy gap. Yeah, it seems to have a finite band gap.
You mean with this?
Oh no, here, from
In the
here to
pristine-
there.
In the pristine case.
So it's a semiconductor, right?
But
Yeah.
what is the size of the gap? Approximately, like
You can look on your finger, right?
0.1 electron volt, 1 electron volt, 10 electron volt.
Two.
Okay,
Around
So,
2 electron volts.
so about 2 electron volts. So what happened when you put some species on top of it?
It decreases.
So the system still a semiconductor or it become a metal?
It's a semiconductor, but I believe it's a semiconductor.
what does happen to the gap?
It decreases.
But it
Would
still
it,
exists, right? It's not completely going to zero.
Yeah.
okay,
So it's still a semiconductor.
But then whether it's a semiconductor or not, it also depends on the position at the Fermi level, right?
Okay.
but you are telling that it is not going to, it doesn't transfer to the metal. It is still a semiconductor, at least what you found. Okay, let's thank Whitney once again. So we have, next speaker is Jabir Abu Mohammed. So please set up your presentation, and he continues the description of the electronic structure of nanomaterials, and he will be looking on the interface between metal and semiconductor. We have 4 talks for about 20 minutes. Floor is yours.
And this is gonna close at 2 p.m.
Yeah.
So
Yep.
more time. So I'm gonna talk on the initial state of the metal and metal interface for resistive switching applications. So since the resistive switching is a new thing, some guys so first let's start what is actually resistive switching. So if you're gonna start on the electrical, they have a 4 parameter voltage, flux, and current and charge. So if they have a, if you're going to make a relationship, we got a 3 different circuit, but still they have a one relation between the charge and flux missing until 1971, or in the Dr. Liu's on, he mathematically derived an equation and formed that maybe there have should exist a circuit which is called a memoristor, and it's practically prepared in 2008 by HP scientists. So how this actually switching is works? So is the device, if we increase the voltage, voltage in a positive direction, the conductivity will increases, and it can keep memory that conductivity. And if we put the reverse bias, it will give you that previous resistance. So we are going to make devices with these properties, but question is why we need these properties. So in a one line, one sentence, this recent semiconductor-based technology, it's almost in the theoretical limit. After that, so we need new mechanisms. So it would be the replacement of these devices, and it would be can be used for like neuromorphic device designs. So to do this one, I consider my models. My models actually I am considering one titanium oxide layer with one of the metal oxide layer on the top of them to study these properties. I studied this system on the bulbs using methodology. To do that, this one is giving us a pristine only metal oxide layer with the metal layer and this one is I replace one titanium with the aluminum in the titanium oxide layer to see how it changes their conductivity. I also studied the study the oxygen vacancy, how it changed the conductivity, but I didn't actually complete on this system, so I just work on this too. So first one, this one is giving us a 2D presentation of the orbital, how the electron localized in which part, in which layer, metal oxide layer or in the metal layer. So this one is showing the